I guess I should be recording. But up to this point now, we've gone through and looked at, you know, the small, what you call small signal amplifiers, right? So these wouldn't be used for any power applications. And I mean, in some of the cases, if you try to go to like a large signal amplification, the distortion on it would be so drastic that it wouldn't even be worth it. But now, so essentially, I mean, so you would even in some cases use like a cascade or even taking like a couple of these circuits, like maybe you would have two voltage dividers with some kind of capacitance in the middle. There are two small signal amplifiers like in tandem. So you would boost the signal once and then boost it twice, possibly go through something like what we had with lab 4. If you noticed in lab 4, what was your amplification overall, right? It didn't really look like there was any if you looked at it overall, and it was almost like a reproduction of the original signal. And the reason they do something like that, there's a term they have where it's unity gain. And a unity gain amplifier, it is where you have literally like a gain of 1. And then you go, okay, what's the point of that? Well, let's say you had like a noisy signal. Maybe you had like the two small signal ones, but the final output, it did have like a little distortion to it or something like that. And then what you could do is send it through a unity gain amplifier where it would take the original signal and reproduce it, and without like any of the noise or distortion to it. So it would produce like a nice, clean, smooth signal. And they use those a lot. That's like basically it's an analog filter. So you would use a unity gain amplifier to smooth out any ripples you might be experiencing, something like that. Excuse me. And then what you would do is you would take that signal and then you would put it into now what we're going to start getting into here in Frenzo's chapter 37. But I'm also going to start with Malvino's explanation, which I feel is a little more straightforward and understandable for everybody. But oh yeah, John, yeah. Oh, absolutely. No, that's what the intent was on that. I mean, you think, oh, I got this large amplification going on, and then your signal comes out being reproduced, right? It's like, what the heck is going on here? Well, that would be the purpose of something like that. Is basically it's like a noise canceling circuit, if you will. And then you would take that signal. Now it's boosted up a bit, so we wouldn't be able to use any small signal amplifiers for something like that at that point, right? Now we go to what we're going to get into ahead here, where these power amplifiers are actually hooked up. These would be the ones that are hooked up to like the speakers. So you'd be getting your outputs now, right? And these are still used. I mean, if you look on some of like radio equipment, sound equipment, that type of thing, you will see a rating on there where they will say it's like a class A, class B, or etc. What class amplifier is being utilized in there. And then you can go, oh, I know what that is. No. but you can. I mean, that's essentially what we're getting into. And that's the one drawback. Actually, this class, as far as the labs go, would have been a lot of fun because we could have actually made our own like audio amplifiers out of this, where we would have hooked stuff up and made our own noises and you know, sound reproduction and that kind of thing. But we're just going to have to go through more. Well, these are with the signals, and with some of the labs, they'll even show you it's like there will be like an output thing where you would have like somewhere where you could have hooked up two leads to. Well, typically those two leads would have been like a speaker, if you will. So these actually do. Now we're getting into the thing where, yeah, this stuff has this is real world application stuff at this point, right? I mean, now we're actually getting into sound reproduction and that kind of thing. And even in the case like the Class C amplifier, they use those a lot for something they call pulse width modulation. And so you would have like pulse width modulation and then of course the demodulation. So we would actually even be setting these up for RF signals, right? Radio frequencies, where in some ways we could even shortwave broadcast these if we wanted to. But we'd have to be careful, you know, we wouldn't want to be interfering with any outside signals and getting the FCC down. No. But we could do, if you did like small signal broadcasting where, you know, you don't have a lot of power and it's just really like within your house or within a lab, that's totally doable, which is kind of the fun of it too, right? It's like, oh, look, I'm transmitting my own signal and even listening to it, if you will. But we'll still go through. I mean, we'll go through these labs, and then, like I say, we're going to go through the power amps at this point. We'll get through the three, well, technically, I guess it's 4 main classes, where it's Class A, Class B, then a Class AB hybrid, if you will, and then Class C. And Class C's are funny ones. You know, as you'll see when we go through this lecture, those are the ones that are used more for like modulation. They have a really tight bandwidth to them, so you wouldn't just be able to use like any type of signal to it and that type of thing. But yeah, we'll go through that. Let me see if I can get this. Oh, hold on here. Maybe I need to do this first. Oh, good word. Share our screen. All right. Everybody able to see that okay?
Oh, there it is. It hasn't popped up on our screens.
It hasn't popped up?
No.
All right, hold on here. I'm not, oh, yeah, it said sharing has failed. Awesome. I love when everything comes together.
Hey, you know what, though? The internet connection seems better.
Yeah, it's coming and going. I guess they're doing some more out there. Well, the other thing, too, I was saying earlier, on the Zoom software, I guess they, you know, they never really expected to be as large as they've grown in the last month. And I guess their usage went up like something like 600%, they said. So so they've been throwing a lot more resources at this and trying to get rid of their vulnerabilities and that type of thing. All right. Is everybody able to see my screen now, or did I screw that up?
Nope.
Don't see it.
You can see it?
Not see it. Nope.
Nope. Oh, what the hell? All right, hold on here. Screen sharing has failed to start. Awesome. Well, let me try it.
End of class.
Yeah, I know, right? It's like, what a pain. I'm going to get very angry with this. All right. How about now?
Nothing yet.
Oh, what the hell? Yeah, it sure is having trouble. Oh, awesome. Just fantastic. Let's see if I can share this. Hasn't said it failed. Do you guys see my lab at all or no?
Nope.
Oh, what the hell? All right. Fantastic. Let me try to. Yeah, screen sharing has failed to start. Please try again later. No, that's not an option. Fantastic. Huh. What the hell? Still nothing, huh? Hey, this is so impossible because I can't tell what the hell I'm sharing here. You guys don't see anything other than my ugly mug?
Nothing yet.
No.
Seriously. All right. Let me try it. Oh, there. Now it tells me it's like, okay. Let me try closing these stupid screens out and see if I can't get it restarted here. But anyway, so now we're going to go through, this will be such a fun lecture. Let's see here. I can get this thing to pop up. Oh, I swear to God. All right, now I'm not having fun anymore. Do that. Now you will share the screen and you will enjoy it. Make sure my stupid things here. Oh, I'm monkeying with it. I'm sorry. And no more comments on how many times I say I'm sorry. I'm reading that chat screen too now. I'm getting better at this actually. So hold on.
No excuses. You're not Canadian.
No, I'm definitely not. Actually, you know, my family goes back. I don't know if anybody's ever used that. No, what the hell is that called now? The Ancestry.com. I guess my family's been in Illinois since the very beginning. It's kind of interesting.
Do you go back to the French?
No.
Then you're not the beginning. Sorry.
No. The beginning of United States. How's that?
How about my French ancestors actually came from Montreal to Illinois in the 1600s? Beat that.
Well, I can actually. I had I do have the Revolutionary War flag thing on my ancestral background. So my family landed 1649 in North Carolina colony, and then I'm on actually both sides of my family, my father's and my mother's, and then so I'm pretty much like an English Isle mutt, and yeah, Tom Brown. But yeah, the Browns were one of the very first in I guess in an area called Franklin, Illinois, way back when, which is kind of south of Peoria. But they were there when that was while the state was just opening up, if you will. I don't know. That's all. Anyway, but no, I don't go back to the French. No French here. I guess I'm an original American. No. The screen sharing thing is really starting to. Anything now?
Nope.
Seriously.
Seriously.
Screen sharing has failed to start. This is so freaking great. I don't even know how to do this now then.
Which PowerPoint are you trying to share?
I want us to pull up Malvino's chapter 10, which is on today's tab. So I could, it's going to be so boring, but yeah, I guess if you follow the PowerPoint, Malvino's Power Amplifiers, chapter 10, if you will, where we talk about the types of coupling, load lines, transistor power ratings, AB, and then C's. And we look at everybody able to get that, at least. That'll be something. Otherwise, I can just prattle on like a crazed person. All right.
I can try and present from my laptop if you want. I might have a better connection.
There's one thing I did want to ask you, Tom. If you get a chance, the labs are kind of spread out between the days. Would you mind throwing them in like a folder in the assignments folder?
See, I was trying to. So see, the last 8 weeks, that's what I kind of did, right? So you guys would prefer would it be better to have all the homeworks under a homework tab and labs under a lab tab and quizzes under the quiz tab, or would you rather have it on
Yes, please.
on a daily folder type thing?
Do it.
Yeah.
Do it under like labs under lab tab, homework under homework.
We do
tab.
like that.
Do it like that.
Yes.
So then just keep like the daily topics and whatnot, lectures and all that under the daily tab, and then assignments under the individual assignment tabs. Ugh. I can do that.
I don't mean to make a whole bunch of work for you, Tom.
It's hard to keep track of everything.
You guys
Yeah.
make a whole bunch of work for me anyway. I
We-
think that's the point, right?
We don't have a
Just hold
chapter
on.
30. Oh, sorry.
No, you're good. Go ahead.
I was
On a
going to say I'm
chapter-
trying to share my screen, but it says host disabled participant screen sharing. So you might have
Hold
to
on,
flag
hold
me.
on. I can. I've seen somewhere where I could do that. I know I can do it. Hold on. Just bear with me. How the hell do we do that? Multiple per.
We don't have a chapter 37 quiz yet, do we?
No, not yet.
Okay. I was looking for it and I couldn't find it. So
Who can share? All right. Who can start? Who can start sharing when someone else is sharing? Oh no, we don't want that. So one participant can share at a time, and all participants can share.
Boom.
Ah, awesome. I wonder now
Let's see
that
here.
should record that way, right? Maybe.
Now,
It should.
and I believe you can actually give Tom control of your screen, possibly.
Whoa. He doesn't need to know about my furry porn links.
Yeah.
Ah, yes, that's very true. Oh God, I love you guys. All right. So
All right.
here
Mute
is
me.
the secret's out, Ryan says. Okay. So yeah, here we see so the topics we're going to cover, right? The types of coupling that we're allowed to do, our load lines, what are transistor power ratings, and the various, there are actually further classes than this, believe it or not. They go down quite a range in the old alphabet, but they're not very commonly used. These types are like pretty much the main classes that are utilized out there. Excuse me. All right, there we go. So what kind of couplings do we have? So you can have a direct, where it's just your straight DC in, right? And then you've seen like in some of the labs where if we had like the 2 voltage dividers and they have a capacitor in the middle, that would be a capacitive type coupling, okay? Then you have this case where you would have what they call a transformer hooked into it, okay? And it would be untuned, meaning that it could pretty much take in most types of analog inputs, if you will. And then, of course, there's a tune type as well, where that one's more specific, and it would be a very narrow bandwidth that it would be allowed to have. Go ahead and click that again. There we go. So now you've seen this type, all right, in lab 4, where we had the cascade effect, and this is a direct coupling. There's nothing in the way from the emitter side to the base side, right, from Q1 to Q2. So our input just flows directly into that, unfiltered, if you will. I mean, we had filters on the beginning and the end, but nothing in between the two. So it does have applications. There are times when, I mean, the unfortunate thing is if the Q1 were to have like a noisy output, of course, that would transmit directly to Q2. So there are drawbacks to this. All right, go ahead and click that, Brennan. And here's where I was talking about where we've seen the capacitive, where we literally have, if you notice, there's literally 2 bias circuits with this, right? So we have a voltage divider on the left and we have a voltage divider on the right. And In between the two, right, you'll see that C2, and there's our capacitive filter. So he tries to alleviate any type of feedback or noise from the first circuit to the second circuit. Doesn't always work, but it's a passive attempt, if you will. All right, go ahead. And here's a transformer coupling directly in the collector, but there is no tuning for this, okay? So if you were to put, see like the two open ends on the right-hand side there of that transformer, so if you hook up some device to it, what's gonna happen is it's literally gonna take whatever device you had and it's gonna transmit that signal directly through without any kind of filter or anything. So if it's a noisy signal or whatever, it's gonna pass right through, if you will. Go ahead, Brenna. And then this is a tune style where they go ahead and now it's an LC circuit or an LC filter, right? So you have that capacitor on that side, and it attempts to alleviate any kind of noise that might be, yeah, right in there, and alleviate any noise, and then that would pass through and go to the transistor for amplification and then pass through, depending on our circuit setup. But those are pretty much the two types for using a transformer or inductor style, if you will. Go ahead and click us through. So now we get into, and this actually, the cool thing about using the formulas for this actually applies to a lot of devices that you're going to run into out there. But what we have to look at when we look at our power ratings, right? And this is also something that we didn't look at so much on the spec sheets before, but a good thing to note is the first point, right? The power rating of the transistor decreases as the temperature rises. Like I always said, that heat is always our enemy, okay? The higher the heat, the less the current that we're allowed to flow through. So in the same case with transistors. And that's why a lot of times you'll see like the big power transistors are different than the little 3904s that we used. If you remember when I passed them out, these are the type that have like a backing to them. And these types can be hooked up directly to a heat sink. In some cases, they're actually allowed to freestand. It's really up to the engineer to decide how much heat's going to be generated and how much dissipation that they're going to want. But the higher the heat goes, the lower the power rating or the efficiency of your transistor goes. So in the data sheet will list it out, and it'll say what the normal operating temperatures are. And it'll even go, usually, it'll go through and show you at higher heats what kind of derating factors you would have to apply. So a lot of times you can use heat sinks, and sometimes you'll see some really giant heat sinks with some of these power amplifiers. Excuse me. But okay, next slide, Brenna. And here we go. So what are we looking at here? So our maximum power rating for a standard, 25 degrees Celsius. And as it goes up, you see the second point, right? It says decrease in rating is equal to delta P, which delta is something that we use in calculus. Now, what that signifies is really all it's saying is a change in P. So what it's trying to look at is basically all ranges. So this formula would be good for whatever temperatures you're trying to look at. So we look at, okay, what's our derating factor in this case? So if you look at the very bottom, right, our change in P, we would look at what temperature that we would have. Like, look, so our normal operating would be 25 degrees, but let's say we're operating at like 35 or something like that. So then we would have to basically throw in that numbers, right? So 35 minus the 25 and come up with a 10 and then multiply that with the derating factor that we would have. And that would give us our delta P, or what our operating point would be for this transistor. Click the next slide, Brenna. So, and everybody's used to using this transistor, the 3904, but let's say, yeah, it's operating at 35 degrees, which is 10 degrees over what the spec sheet says is its normal operating range, okay? So what we have to do, and we'll go through and multiply out, and we'll see how much loss that we could have. Excuse me. So the 10 degrees Celsius, and the reason they draw the symbol in there, you notice the symbols cancel each other out. So really all we're doing is multiplying the 10 by the 5 milliwatts. and we come up with a 50 milliwatt decrease in efficiency of this transistor if we operated at this heat range. So these are things that have to take into effect, or if you get like a cheesy, I don't know, cheesy radios or something like that, and you'll notice sometimes if they do start getting really hot or something like that, that your audibility starts going down drastically. Well, this would be the reason why. Go ahead and click our next slide, Brennan. So, and as you've noticed up to this point, right, we do have a DC bias and we have an AC bias for a proper amplifier. DC bias to turn it on, and AC bias as our signal that we're going to push through. Now, and I know you guys are going to love this. We all love cue points so much, right? So now we're going to look at 2 cue points. We're not only going to look at the cue point for the DC response, right? We're going to be looking at the cue point for the DC as well as the AC. So, and this becomes very important for us because, again, you know, if you remember from before with the DC, that the cue point was the ideal operating point for this circuit or this particular transistor. Well, and again, that applies very much to this as well, but now it gets a little more interesting. So when we look at the cue point for like the large signal amplifiers, we absolutely have to, see how it says this, we have to be at the center of the AC load line to get our maximum output without clipping, because clipping would take away from our original signal, right? So it'd be something we wouldn't want. And here's a good example. So the first part that we're looking at is, you notice we're, again, all capital letters, right? So this tells me that we are doing DC. So our DC response overall is from the, you know, notice again, we're using IC compared to BC. So saturation to cutoff, right? So our ideal point would be in the middle, okay? So we look at the DC bias for the circuit and ignoring the AC for this point, and we go ahead and draw our load line. So this is our ideal response, right? Maximum IC is the saturation, and of course, maximum BCC would be cutoff. And so ideally, we're going for that middle range, right? All right, click the next slide. So now we look at our AC response in relation to our DC response, okay? So in this case, now we're going to look at, again, both IC of saturation and BCE of cutoff, and notice that we're using the approximate model here, right? Again, remember, short out all capacitors, ground out any DC supplies, redraw your circuit, and this is your response, okay? As from an AC driving point of view. And all we're using here is Ohm's law, right? So we go ahead and calculate out, okay, what is our IC saturation in this point? Draw the point on the IC side. What's our BCE for AC cutoff? Draw that point, draw a line in between. And notice where it crosses over from the AC to the DC becomes now our ideal cue point. So now we're looking at the DC and the AC optimally together and noting where those two cross over, that's our maximum range or our maximum point of efficiency for this particular transistor or circuit, if you will. So that would have set us up and we go, okay, so this is our ideal cue point. So now we know what our ideal voltage ranges are and such like that. All right, go ahead and click the next slide. Thank you. So we calculate through our knowns, right? And this is using the voltage divider. So starting at, you know, and this is looking at the DC response first. So starting at what's the voltage across R2, right? Using the voltage divider rule with the 12 volts, we come up with 4 volts being on R2. And then knowing that, so we minus out the 0.7 drop across the VBE of the transistor and develop our voltage for VRE, which is the 3.3 volts. And since we have that voltage across that RE resistor, now we can develop what our IE current is. And since IC is approximately equal to IE, we set that as 1.5 milliamps as well. So now we want to come up with, okay, now what's our voltage across RC? And we see, and of course, it's nice and easy, right? We see that it's 3.3 volts in this case. And then we do Kirchhoff's voltage law going down the line there, right? 12 volt source subtracted from the 3.3 volts across the RC resistor and subtracted from the 3.3 volts across the RE resistor. And the resultant leaves us what's across the transistor at that point with VCE, right? And that's our 5.4 volts. So then we go through and now we develop, okay, so what's our RC? And remember now, RC is our impedance factor. And so that would be what's our AC response for the RC at this point, at that junction, right? So if we develop that through, we come up with what we have 1.8 kilo ohms. So this sets us up for our knowns. And basically, you know, this comes from the previous slide where we developed out what our IC of saturation and our VC of cutoff, and that's where we developed that out. So it wasn't just like pulling it out of our butts, okay? All right, next slide, if you will. So, and there's everybody's favorite graph. I know. But, so the first part, of course, is we're drawing notice the headline, right? DC load line. So we're drawing our DC load line from our saturation point to our cutoff point and drawing a line in between showing our response overall. And the blue lines, remember, that is the ID current for the transistor, just so everybody remembers. I want to make sure we're all on the same page. So going through, and we're just really, you know, like I say, we're using Ohm's law in this case. So our IC of the saturation is the VCC divided by what? Two resistors, RC and RE. So I developed through and we come up with just a little under 3 there, right? The 2.73 milliamps. And then at cutoff, our VCE is equal to the VCC. So that makes it nice and simple for us, right? So we just simply draw in, oh, well, it's 12 volts. Exactly. So then we just draw a line from our response all the way through. And ideally, okay, then we come up with, now we'd have to come up with the ideal Q point of the DC load line, right? Next slide, Brenna. So then we look at our AC response and notice it is different, right? So, and this is where we come up with our points. So we look at ICQ, the VCEQ, and divided by the RC. These are all AC response points at this. So we'd have to use that approximate circuit when we go through. And remember that these resistors are all going to be in parallel. And coming up with RC is like a beta RE, if you recall. So these are all formulas. I will post, I will try to make sure that we have all the formula sheets as we go through these different circuits so that way you guys aren't, I don't want you to reinvent the wheel. That's just silly. So we'll do that. And then that way you can just plug in numbers and go through your circuits and, you know, be able to see, okay, what's my response to this? So really what we're looking at, so again, we're looking at the IC of the AC saturation, right? And we come up with 5.73 milliamps, just a little under 6 there. And notice for the AC response, you know, the VCE, of course, isn't going to equal VCC because we have no VCC. That's been grounded out for our AC in this case. So now we got to do a little Ohm's law juggling, right? So we have, you know, these aren't unknowns. We have the ICQ, we have the RC, and we have our we have our VCEQ. Remember, these are also available on our data sheet. So we wouldn't just be pulling these numbers out of our butts. We'd look these up, plug them in, you know, depending on our transistors. Of course, with the simulator, we're using ideals, so it won't be all that difficult. We'll be able to use ideals for everything. But in a case like this, this is the 3904, which we were somewhat used to using in the lab. But in any case, so we draw the AC load line, and then you see the 2, right, as we cross over. So we don't have to go through and plug through, okay, what's our typical area for the AC for the Q point, and the same with the DC. Now we just look for, okay, where do they cross over? And at that point, that is our ideal. So that would be where we would want our operating point to be for our circuit. So we would have to look through and see, okay, what's our magic number here? And you can see it's for for BCE, that it would be a bit over 8 volts there. And the same with the other side, you know, so what's our IB in this case, and what's our IC going to be, and that kind of thing. So this would set us all up, and then we could go through and plug our parameters to see what our ideal operating point. for the circuit would be. Next slide, Brenda. So then we start looking at our first one, right? The Class A amplifier. Now, Class A's are kind of interesting. And remember, each one of these, as we get through it, they're all used for a little bit different types of applications. I mean, Class A's, what their ability is they can basically they can convert their DC power that you have into useful AC output. See, now all these amplifiers, you're not going to be able to do that. There's going to be different applications for these, if you will. Some of them we might be running in saturation. Some of them we might be running in cutoff, but they all have useful applications. But now the Class A, the great thing, and that's why we're coming up with the ideal Q point for these things, right? Is to find out what is our ideal operating point for this thing so we can convert our DC and use that power for this. So if we look, okay, we come up, now we're going to start looking at like the power end of things instead of looking at what the voltages are and this and that. So in our classic Joule's law power formula, right, P is equal to E times I. So in this case, the P of our DC is going to be the VCC multiplied, of course, by the current of the DC. And we'll have to look at, now this formula is interesting because this actually applies to a lot of things, but the efficiency rating that they use, here's another Greek letter for you. And this is the lowercase, but what that is ETA, it's ETA. So we say the efficiency is equal to ETA, which is equal to our P out divided by the power of the DC multiplied by 100. Now, this will give you a rating, and you'd be able to see, okay, what's my efficiency? And of course, there's no way, given that we're going to have a ratio here, there's no way we're ever going to have a 100% efficiency, okay? So never, ever expect it because it's not going to happen. If you notice on his next line, he says that the maximum efficiency for Class A's with the DC collector resistance and separate load resistance is 25%, which would seem it's, wow, 25%, that's not really much, right? not so good. It's like, oh my God, why would you want to use this? But, and even next point, right? It's not acceptable when you have large amounts of power, or, because you're not going to get it. It's just simply not going to pump it through, if you will. But we take that in mind, and there are applications for the Class A when we would want something like this. And granted, always remember, your efficiency rating. Is this thing really going to deliver for me? But there are, there's applications, but these days they start to go further away with different integrated circuits and whatnot. But you will run into Class A amplifiers out there. They still do have applications. I can't think of off the top of my head, but next slide, if you will, Brennan. So we look at, okay, and now remember before we were looking at like the small signals, what were we concerned about? We were looking at A sub B. Now we're going to look at A sub P, because now we're listening and more interested in what our overall power output's going to be. Because now we're actually getting into like a halfway decent sized signal instead of like, something in the millivolts. We're actually going to be in the volt ranges, right? So like from that last lab you had, what was the output, right? 2 volts peak. So that would be considered a large signal. And so if we're going to be doing something like that, we're going to be looking at it from a power point of view. So in this case, just like with the voltage, you weigh the output versus the input. So we'd have to look at what's our power out compared to our power in. So, and I mean, of course, the power rating of a transistor has to be greater than what's a quiescent power dissipation, right? The Q point of operation. So, and we're going to look at that with the efficiency formula that we just had there, what's ETA. Always remember that with ETA, because that is going to follow you through. They actually use that, you'd be amazed. They use that same formula as used for like AC motors, if you will. What's the efficiency rating of this motor? So that formula is something you're going to see pop up quite a bit, and it's a classic for power efficiency rating on how to figure out how good is this thing delivering for me, and And you'll see that with motors when you get into 150 and stuff. And I'm not lying, that you will use that same exact formula. So yeah, your efficiency is well, like in this case. So Class A's, we know we're gonna lose. We're gonna lose. But Class A's got a unique thing, and that it's going to allow 360 degrees of the cycle through. So how do we look at this? It's like, why is that one drawn on the side? And it's a comparison. So we're looking at our AC signal inputs, right? So you notice we're doing 2 alternations, which would be 360 degrees. And notice the phase difference between the two. Because of course, we're dealing with, what do we weigh here? We're looking at current versus the voltage. So yeah, and just remember with a Class A, it is going to allow through the full 360 without any clipping. Okay, we don't want clipping in this case. It's not the point of this type of amplifier. If we do experience clipping, that means we're overdriving this particular circuit. But always keep that in mind. This is one of the golden rules of a Class A. The 360 degrees of the AC signal is kind of an important thing, and it relates directly to our Q point. Next slide, if you will, Brenda. So now we look at, this guy's a little different. Class Bs are weird, okay? I'm not gonna lie. They have an odd configuration and almost, oh God, I want to put a percentage of it, but over 90% of all Class Bs are in what they call a push-pull configuration. A push-pull is like is source sync. And what does that mean? So essentially, Class Bs usually use 2 transistors, if you will. And when they're running in a push-pull configuration, one is on, one is off. So, and they alternate back and forth, okay? One will be on, will you hush? One will be on and one will be off. And the unique thing with this one, notice compared to the other one, we're allowing 180 degrees of the cycle through as compared to 360 degrees. And in this particular one, notice that we identify that the Q point is going to be located at our cutoff on both the DC and AC load lines, which makes this really easy for us. We'll be able to look, I mean, we don't even have to do, yeah, look at this. So, and notice, what are we looking at here? Notice the first thing, oh, we have clipping. So in this case, we're only using, like I said, the 180 degrees of the AC cycle. So like I said, one will be on, one will be off, and then vice versa. So, you know, during the positive alternations, this one will be off, clipping the negative, and then vice versa. So as far as the math goes with these guys, it's pretty straightforward. Really all you're looking at is, okay, what are we running at and cutoff saturation? It's like boom, boom, and we just jot down our numbers. Next slide, if you will. So in classic push-pull configuration, now remember, push-pull, on, off, on, off. So whenever you hear that term, push-pull, just sync, source and sync. And what that means is, for like electrically driven, so on and off, one is sourcing and one is syncing. And what syncing really means I'm acting like a ground point, if you will. Okay, it's not really, it would almost be a way to think of like I'm a virtual ground. So one is sourcing, meaning he's driving out, and one is syncing, meaning he's acting like a ground or clipping, if you will. So in a push-pull, each transistor is going to conduct for half the cycle. And we don't have to worry about bias, right? Why? Well, if we're going to be running in cutoff, there is no bias in this case. And notice, with the Class B, what's our efficiency rating on this bad boy? We're getting almost 80% out from this thing, okay? And you typically, and there's another key note, almost always, transformers won't be used with these guys. They're, you know, they'll be bulky, expensive. You won't have to use it to balance out like in the Class A type of thing. The Class B configuration almost has its own noise canceling, if you will, just because of the way the source syncing. So while one is sourcing, the other is syncing. Next slide, if you will, Brenna. Yeah, here we go. So notice how we have this hooked up, right? We have a center tap on this, and the same with the transformer. We have the center tap. So, and like I said, so one will be on, one will be off. And notice that we use both styles of transistors with this. See, I'm so excited. With the PMP up on the top and the MPN down on the bottom. So while one is on, the other will be off, and vice versa. And notice what we have on our output here. We actually have a speaker hooked up. So you're literally, with this type, you can see that we're definitely going to be doing some work with this guy, and you'll be allowed to push. In fact, this very circuit is a real simple one to build. Well, you can see, look at the components here, right? These are a lot of times, these are the types that they'll use when you have like a very simple thing like a toy or something like that, that's just making that little warble sound or something. You know, you have a fire engine or something like that, and it has that little cheesy little tiny speaker with it or something. This is the type of amplifier you would use with something like that. It's very cost effective. I mean, we don't really have much to it, right? We have the 2 coils in this case, 2 transistors and a speaker with hooked up to some kind of input. In which case, you know, if when we do later, we're going to get into oscillators. So if we just hooked up a simple oscillator to this, right, you literally would make your own siren effect where kind of thing, you know what I mean? Which is a sad thing for me, because this would have been a, you know, kind of a fun one to do in lab, where we would have had like a frequency generator hooked into the VN, and you could literally by hand go ahead and like I said, it's so annoying, but, and here we go. Now, oh no, that's good. So here we see a little more complex, if you will, push-pull amplifier. Notice that we're using the emitter follower style, but notice that on the output, this one experiences a certain degree of distortion. And they try to balance that out with the capacitors, but in this case, I mean, you're literally, you're getting like, there's like a lull in between the two, if you will. So we don't get a clean output with this case. So notice we have the, you know, again, same deal with the push pulls, right? One is on, one is off. And notice that, you know, what we have on the input. And because just like the diode effect, right, where we get that 0.7 volt drop with VBE, we're going to experience that same thing with this. So we get that lull in between the times, because one is on and one is off, and vice versa. And in that lull, that's when you get this crossover happening, like you do, where the signal looks like somebody just chopped it up a little bit, right? But this is a very classic, and again, remember the efficiency rating of these things. And even with this, it's still very, very simple and cost effective, because you have not very many components, and you can drive out a direct signal with this guy. And in which case you would have something hooked up, you know, where you have the load resistor, and that could be channeled out to, again, like some little speaker or something like that. But, and this one would almost make its own weird, well, you would have to almost hear the warble it makes. But remember, yeah, with this style where you have the emitter follower configuration, you are going to experience a certain amount of crossover, you know, because there is a certain amount of distortion that always goes with the emitter follower. The emitter follower likes to clip, if you will. So when we already have a certain amount of clipping occurring anyway with the push-pull, the emitter follower's clipping also adds into that, and that's what creates that output signal like that. Next slide, if you will, Ben. And then we look at these. So this is like a hybrid one. So we've seen that experience that crossover distortion with that final circuit there. So we try to kind of incorporate some of the benefits of a Class A to some of the benefits of a Class B. And if you notice, in this case, we got like an in-between point, right? So we won't experience the full clipping like we did with the Class B, but at the same time, we don't get the full signal follow-through like we did with the Class A. Now go ahead and hit the next slide and we'll show you. So the transistors, it does have a certain amount of bias to it. It's a lot closer, instead of being like with that Class A where you're kind of more in the middle as your ideal cue point. This one's going to be a lot closer to our to our cutoff. In fact, I mean, it's just like a hair above, but now we're not going to be operating in cutoff anymore. So now the actual beta of the transistors are going to come into play. And if you remember, of course, beta dependency is not always a good thing. So, but the one thing that we can do by setting what our ideal Q point in this case, we try to eliminate some of that crossover distortion. And in fact, this is kind of unique. Next slide, if you will, Brenna. We look at, we're going to be using diodes with this guy. And just remember with the diodes, we do have our reverse and forward bias, right? 2 states of a diode. So with the diode biasing, what'll happen is you never will fully allow a transistor to go completely off with the classic push-pull. Because in classic push-pull, you know, when you turn the NPN on, you're turning off the PNP and vice versa. Well, with the diode going in there, remember, we have that 0.7 volt drop across the diode at all times, right? So what that'll do is it sort of still keeps the PNP on while the NPN's running and vice versa, but not fully on, if that makes any sense. So we will get a small amount of collector current, but I'm trying to think how to. So we won't get that lag time. Remember, like in the signal before, where we had it, where it looked like, okay, during the negative there was a lull in between the positive cycle and so on. But it will change your signal overall. Next slide, if you will. So we can see here we still use the push-pull style, right? But notice in between, now we have 2 diodes tied in here, where, and of course, remember where the way they work, right? We get either forward bias or reverse bias. We get the 0.7 volt drop across. And in one case, and remember how it does in reverse biasing. So like I said, the way this configuration is with the AC alternation going in with it, yeah, it never lets either of those transistors turn completely off. So at all points, they're still transmitting somewhat, just not ideally, if you will. So your output signal, and we will do, I think I do have a lab for this, so you'll be able to see what exactly it does. You know, you'll be able to play with it somewhat and be able to see how it interacts with the output of the transistor, if you will. Next slide. And of course, can't do it without doing a whole bunch of math, right? So we have to decide, okay, in this case, because we have the diodes in there, we have to decide what's our bias going to be in this case. So the way we look at it, it becomes kind of interesting. And again, I will post formulas for these guys, so you don't have to, you know, like I say, reinvent the wheel. So we'll get all those posted up. But if we look at establishing what our bias current is going to be, so how do we look at it? How do we approach it? So in this case, we're going to have 2 VBEs, right? Because we have the 2 transistors. We have a 20 volt input signal. And we have our two load resistors. We have R1 and R2 on that side. So remember, this is like a voltage divider circuit, sort of, kind of, sort of. But remember, you know, you get 0.7 volt drop for each diode, and we have 2 of them. So we have to incorporate that through and decide, okay, so what is our bias current, or what's our current going to be on that that left leg as a DC standpoint here? So we look at it and we'll say, okay, this is 2.38 milliamps. And what that'll allow us to do is be able to decide what kind of voltages we're going to have on both R1 and R2 in this case. It's an odd configuration, but in this case, we are incorporating, you know, both things from the last 8 weeks. Now we're using diodes in this to help kind of control or alleviate the crossover distortion for this. Next slide, if you will. So we have to decide what our saturation is going to be, because we're not in saturation, but we are operating really close to this thing's extremes in this case. So with knowing what our bias current is on the outside there, now we decide, okay, what's our saturation for IC going to be? Because notice on the outside there, right, on the right-hand side, there are no resistors to develop any types of voltages for either Q1 or Q2. So these are going to be totally current driven as far as those go, right? You won't be, if you put a probe on there or something like that, you're not going to see any voltages per se. But you would have to break the line, and you can see what our current, our operating current is going to be. Next slide, if you will. I really appreciate this too, Brenda. Thank you very much. All right. Oh God, you guys are gonna hate me so much. So now we decide, okay, we've calculated through what our bias current is on the outside leg. We decide what our saturation current is on the inside leg, right, running with Q1 and Q2. And now we're gonna try to average these bad boys out. And if you remember, okay, if we look at one full alternation, right, 180 degrees, that's where we get the pi value. So that's why we're going to use that. That's a full run. I mean, if we were going at the halfway point, it would be pi over 2, and then the midway is 3 pi over 2, and then finally 2 pi, right? But in this case, that's why we throw pi in there. So we're going to try to use this to calculate what our average current is going to be. And notice that these are all in lowercase letters. So this is figuring out what the AC response is, if you will. So we divide the collector, right? The saturation current, which is 1 amp, we're going to divide that by pi, right? 3.194, and come up with 318 milliamps as our average current. And why would we need to see that? Next slide. Has helped us figure out what our overall response is going to be of this circuit. So now notice we have 3 separate currents here in this case. We know what our I bias is, we know what our saturation current is on collector, and we know now what our average current is going to be here. And we would like to, well, I'm going to draw you a little picture here. So if we look, and now we're going to decide what is our overall DC current for this particular circuit. And we're going to use both currents that we came up with, right? The saturations on the C side and the bias on the right-hand, the left-hand side there, if you will. And we're going to add those together to come up with, like, oh, how would you look at it? Sort of like an overall current, if you will. So you can see that, you know, since the 0.38 is so small, and by comparison, we're already in milliamps. So you basically are taking 318 milliamps and adding in the 2 milliamps from that side and deciding, okay, this is our DC delivery in this case is 320 milliamps, if you will, for this particular circuit. Next slide, if you will, Brenda. And our main goal, remember, is to be able to figure out what our power delivery is for this guy, right? We're going to go like basically like we did before with the other circuits, but we're going to go one step past. And now we're actually going to figure out what our overall power delivery is. So in this case, we've gone through and figured out what our average current is, our bias, our saturation, and now what our DC current is. And now we're going to look at what the DC power delivery is able to be, right? So E times I, nothing major. You go with the DC because we're looking at the DC. So our BCC in is 20 volts multiplied by the 320 milliamps, right? And we come up with that our power of this circuit as from a DC point of view is 6.4 watts, which is a pretty decent range. I mean, we're not dealing with milliwatts or anything. This is actually, you know, some power delivery we have going on here, right? Next slide, if you will. So now, of course, so if we have the DC, well, what the heck is our AC? And here we come with, now this is a formula too, by the way, for the P out for AC. Notice how it says max. And what the hell is MPP? Well, that's our maximum peak-to-peak voltage in this case. And we could go through and do the math and go figure out why are we doing this combinational circuit. And what they do is we start with, if we look at it from our volts RMS value from the very beginning, and remember we have to convert. So if we were looking at an RMS value, we would have to convert to do a peak-to-peak value. And that's what's going on in this circuit. It isn't just like magic that they go ahead and, well, we're just going to throw a number 8 in there and do it like that. No, since we are, and again, you know, normally what this would have been, where we come up with the square root symbol, it would have been the square root of the P out is equaling, you know, the volts RMS and divide it out, right? Basically coming up with the E times I formula. But by juggling it around with the VRMS to peak formula, that's how we come up with this guy. So essentially what that is maximum peak to peak value of what your AC input is there, right? So we square that and we divide that by 8 times RL, which is your output load resistor in this case. So we have our, so we look in this case, so our maximum peak to peak is 20 volts, and we can see that our load resistor is nice and small, so 10. So we do the math and plug it through, and we see that our AC output in this case is 5 watts. Again, nice. I know that's actual work. We're actually getting some juice. Next slide, if you will. So now we're going to look at what's our overall efficiency for this bad boy. Well, let's do some ratios, if you will. So again, we throw in our magic little Greek letter there, eta, right? ETA. This is the lowercase version of that. And believe it or not, the uppercase doesn't look anything like an N like that. But anyway, so we do our ratio. So we're going to look at what our P out max in this case, right, was our AC, so 5 watts. And then we're going to divide it by our DC value, and we got 6.4 watts, and multiply it by 100%. And we see we get actually a 78% efficiency rating. So we don't have a whole lot of power loss. And you got to remember too, you know, when you look at these things, where's your power loss come into play? Well, a lot of that, believe it or not, is the heat. You know, if you look at any type of typical power amplifiers, there's always a lot of, oh, scared me, a lot of heat generating. And that's what's going on here. So you are going to experience loss in the form of heat and a few other things, but primarily heat. And it's so all that heat generating out by the transistors of your circuit as it's going through its work, that's where your power loss is being experienced. So in this case, I mean, getting out practically 80% is a really good delivery, more or less. Anyway, so next, and then we come up with, and here's a little oddball one, okay? Now the Class C is a very, oh, hold on here. Okay, all right, John had to leave here. I will see you later, John. Yeah, I'll have this all recorded and posted up. But the Class C now, he's like I say, he's a weird circuit. He's kind of a, let me think here, good way to, okay, almost all Class Cs are resonant circuits. They're tuned. Yeah, here you go. So they're tuned, okay? And then you notice in this case, it's a tuned RF amplifier, if you will, and it's on a very tight band. So when we design these, see how you say FR, so what is that? FR is your resonant frequency. So when we design these ones, we're locking it in tight. So we do our 2 pi with square root of LC in this case. And you'll see in the next slide that that basically we are tuning it and that it has a very, very tight upper and lower frequency end. So we're only going right in the middle. So we're not allowed a lot of play. So anything lower or higher in the frequency range is going to be rejected by this particular amplifier. And it is negatively clamped. The reason being is because we do want to keep it tight. And so what we're trying to do, excuse me, is keep the collector restricted. We're not going to allow through all AC input in this case. All we're going to let through is what we specifically designed this particular amplifier to do. So there are applications for this. And like I say, a lot of times really all you're doing with these guys, these are tuned amplifiers for specific frequencies, and you would never ever like use them for any other type of frequency. So that's their drawback, of course, right? They're not allowed a lot of variability. But again, if you have something where you do have only a fixed particular output, this would be an ideal amplifier to use because it you're allowed a lot of restriction to it. So you're allowed to get rid of a lot of the like crossover distortion, and if you will, next slide, if you will, Brenda. Yeah, see here. So if you look at our BCC, we have an LC circuit directly in line with that. And you can even see by our response, right, our resonant frequency, we have a very, very narrow range for this, this particular amplifier to operate in. So if you were to go through and try like with your source voltage there, try varying the frequency when you've already locked in, yeah, you'll notice that not much is going to come out except for what you've allowed through, if that makes, you know, again, reinforcing our AC principles, if you will. But this one's nice and easy. You don't have a whole lot to worry about with it. It's like I say, he's locked in as far as the AC signal is concerned. So we just have some adjustments to make for the values of L and C to lock in for that frequency, of course, and then just establishing what we want for our base and our load resistors to be in this case. Otherwise, it's a pretty simple circuit. Yeah, see? So when we do the design of it, right, we're going to design, okay, what do we want our overall frequency to be in this case? So we've already decided, it's okay, so this is going to be our resonant frequency, 1 kilohertz, 10 kilohertz, whatever we've set it up for. And in this case, then we go through and do some design parameters. So we're going to do our Q of our Q, right? So in this case, and one way, pardon me, I need to get a sip here. Talking way too much. One of our things, so we can set it up on our inductor side as we look at our Q, at our source resistance, and then, you know, and since we've locked in ideally what our inductors are, our value already is, we could very easily decide, okay, well, this is what our QL will be, Q sub L would be, and then figuring out what any equivalency. See, these formulas are fixed and they're not that bad because generally speaking, you usually find out what your frequency is that you want to establish first. So then everything else falls into place and you just kind of design your whole circuit around that. And we don't have many values to play with. And again, remember R sub C, in a lowercase like that, is what our AC resistance. And in the same case with this, when we do an approximation or the AC side, we're still going to go through and we're going to short out the capacitors and ground out the DC supply and figure out what our values are overall. And then from a power rating, again, you're still going to go with the maximum, you know, the maximum peak to peak voltage in this case. But notice that the denominator is a little different. Instead of 8 RL, in this case, we're going to use 40 sub RC, right? So in that respect, this does change. But again, this is a fixed formula. You won't have to reinvent the wheel. And remember, when we do this maximum peak to peak, what you originally start with is you're looking at the voltage RMS from your delivery, right? In this case, we would have our generator, you know, function generator or whatever other your source is. But you would then have to convert that voltage RMS into the, you know, the peak to peak voltages, and that's where you come up with these numbers like you do. Next slide, if you will. So class C's are easy. They, yeah, you notice that we're totally running in a cutoff region in this case, right? So as far as figuring out what our DC is at this, it becomes a no-brainer. It's like, well, your DC response is always this. And so where's your Q point crossover? Well, same deal. So the thing to remember, right, from a DC response, what is your VC of cutoff? Well, that's going to be equal to whatever your source is, in this case, your VCC. And then you would go through and figure out, well, what's my AC VC cutoff, okay? And then you would calculate that through. And again, though, remember, our Q point's drawn at the crossover. And in this case, this is right at that junction. So this becomes very easy as well. Excuse me. So the Class C amplifier. So in this case, we're charging up. You know, we do experience a certain amount of clamping. And you'll notice on our output, it's narrow. It's very narrow. And in fact, we're not getting out the full range here. If you look at that at sine wave output. We've clipped, and we're also reducing. And again, so anything that fell outside of that frequency range that we had is literally getting rejected. So you're really only allowed to pass through what you've designed your circuit to do, in this case, the LC circuit. Does that make it, does anybody have any question? I mean, because it does, it's very strange, I know, but they do use these, this would be like something where we have like pulse width modulation or setting up for pulse width modulation. And again, modulation is always using one signal and we would embed another signal within it. So we would be setting this up for basically to be used with something else. And that's why it's all, you generally only use with RF signals, you know, radio frequency signals. Because once we start getting into modulation, then we're getting set up that essentially what we're going to try to do is broadcast. Whatever medium we use for broadcasting in the old days, of course, it was like the radio signals and then TV and so on. But that's what this type of circuit would do. This is a very, very simple modulation type circuit. And you'll only ever really see it used in with RF signals, you know, RF aspects. Outside of that, there's no use as far as, I mean, you can see as far as like a power point of view, it's fairly inefficient. You know, we're reducing and losing a lot of our original signals, so you wouldn't want to use it as a straight power application, if you will. Next slide. I think we're actually getting, yeah, we're getting down to the end there. So, I don't even know how to, let's see here. Guess we do that. Oh, no, we don't. Awesome. I gotta figure out how to do this. Will you dogs get out of here?
What you need?
Oh no, well, I mean, it's up to you guys. I know this is all really dry and boring stuff. Cause and the reason I wanted to go through it from this end, I mean, if you guys want to take a break too, we could keep going if you want, or we can be done. But I mean, I'm assigning Frenzel's chapter 37, and it goes into basically his version of what power application is. And of course, I don't know, like I say, I always find his explanations to be somewhat lacking, I guess. So what I want to do is basically have us go through, you know, of course, go through his chapter 37 homework. Will you dogs get out of here? But I definitely wanted to reference Malvino stuff here because I think his formulas and his usages are much easier. But those are really the only 4 styles that we'll ever commonly see. Like I say, there are other classes out there, but they're very rare, and even some of these you won't see as often. The class B's now you still will, believe it or not, because of their efficiency overall. And in some cases, some of the, like the cheapies as far as RF signals, you will see the class C's in some case, and still with the class ABs as well. The class A, here and there you might, I would typically more expect to see it like on older equipment, you know, stuff from maybe like your grandparents' days, that kind of thing. But more of the new stuff, I wouldn't expect to see a class A in use so much anymore. But no, I mean, we could look at, I did post up Frenzel's thing, but a lot of times, like I say, he leaves a lot to be desired. I mean, our main takeaways from looking at power amps at this point, our biggest takeaways is definitely that the power efficiency formula, you know, ETA, that's a biggie. That one we definitely will want to know. And then like I say, I'll post up like a formula sheet for each type of amplifier, so you guys don't have to reinvent the wheel. And the unique thing is, I mean, each one has their own deal as far as like, I mean, a class A really was the only one that were trying to find an ideal cue point. All the other ones are kind of dictated by saturation and cutoff, which is nice because then we're just locked down and boom, boom, our values just fall into place. But yeah, that's what I want to, so I want to get through this. We got some labs for power amplifiers that I thought were halfway decent. And see, like I say, this takes all my fun out because we would have been in lab playing with speakers and stuff, right? Getting actual real annoying sound output, if you will. But no, it's up to you guys. But yeah, I mean, I've signed the homework, chapter 37. I haven't decided when we're going to do the quiz, and I may, as far as Wednesday, we're going to do a in betweener. Like I said, I really couldn't find it in the Frenzel text, but I want to cover differential amplifiers, if you will, because basically looking at our small signal inputs, and then we look at the power amps and stuff, and then what we look at is differential amplifiers. That pretty much covers like all transistor aspects of amplifiers, right? But then going up, and then the differential amplifier, I feel, is a very good lead-in to go into op amps, and then we'll go into Frenzel's chapters 34 and 35, because op amps I actually expect us to spend the next couple of weeks on after this week. This week I'd like to finish up, like I say, with the differential amplifiers, and then lead into the op amps, and then we'll start looking at op amp aspects and stuff, because there's a few new things we're going to run into. I mean, the source sync thing sets us up a little bit, and setting us up into what a virtual ground is, because the syncing, whenever you sync something like that, it tends to act like, no, and I say virtual and acting like a ground because it's not real ground, but as far as like a signal is concerned, or at least that driving signal for that, it thinks it's a ground. But that sets us up for some stuff with op amps, because op amps operate on that have that principle in there as well, where we're going to run into this, like, what the hell is this virtual ground? Well, we're going to be dealing with that a little more with op amps, and then we'll get into the most famous one of all. We'll start with the LM741, and that was the one that started it all. They came up with the differential one first, using 2 transistors like that, but then eventually when we went into integrated circuits, right, we started making chips. So what this would be, the op amp is essentially an analog chip. So all other integrated circuits for the most part are usually digital chips, right? So stuff you've been running into in Bob's class, like the JK, the flip-flops and registers and things like that. So those would be considered digital chips, but the op amp is our analog chip. And I think the differential will set us up really well for that. Are you guys able to go through everything okay so far? Is there any questions you have on this? Is this too much, too fast? Is okay? I mean, I was kind of looking at it as being a fairly decent pace so far. Oh goodness, is everybody muted? How do I?
Pace has been okay. It's just had a lot of labs to do.
Yeah. Mm-hmm.
Is that too many labs? Am I posting etches?
Yeah.
So many labs. You need less
Too many
labs.
labs. Well, I mean, because it's a lot of different circuits, and the way they, I mean, the biggest thing is to see what these things are doing to the signals. You know what I mean? Because there's a lot of, like I say, 8 weeks is but I mean, I'd like to also for us to get into, because towards the end, there's 3 things that be past op amps that I want us to do, is the thyristors, which is really kind of a goofy concept, and then possibly a little bit on the 555 timers from an analog perspective, if you will, and then, well, that'll come after oscillators. I'd like us to do oscillators as well, because essentially by that point, then you would have pretty much everything from end to end, where you could almost, like if you wanted to build your own radio, if you will, you would have everything from start to finish on what you would need to do, as far as like a transmitter, receiver type of thing. Because you could even make one like that you would use in your house, where it's just like a little shortwave, so say you wanted to make a little transmitter and have it send out a signal, and then maybe somewhere else in your house you have a little receiver type of thing, and then you'd be able to transmit the signals. I don't know, it's just silly little things, but it was kind of one of the cool things about this kind of class is that that's what you would end up with as the end, right? Essentially doing your own little radio, or you could even, I would have wanted to have like half the class build transmitters and the other half build receivers, and then little cheesy microphones and send signals and that kind of thing. But but too many labs. Well, I don't know. What do we have? We're on week 3, and I'm up to 8 labs so far. So what is that? Yeah, there might be a few, but I promise they'll start tapering off a bit. It's just that we had a lot of amplifier like topics to cover, and like with this one with the 4 different styles of class, class amplifiers. And like I say, our biggest takeaways out of all this is getting that push-pull concept down from the 2, on and off again transistors. That concept's important to follow with you, and then and that efficiency formula from ADA, where you're measuring a power output versus the power input, and multiplying it by 100 and seeing, well, what's your efficiency? And then you can actually weigh devices and stuff like that and see, are these things really efficient? Or like in that case of that one where you had 25% as your maximum efficiency. Yeah, that's a lot of power loss there. Why would you want to do something like that? But there were applications at a time for that. But yeah, these things crank out heat. But no, that's really where I want us to go. So I promise the labs will start tapering off a bit. Like we'll do, we'll finish up transistors. Our final one there, you'll know you're at the end of transistor labs when we get the differential amplifier will be the final one. And then from that point, then we'll start taking a little time because the op-amp concepts will we'll start looking at that. We got 2 chapters of op-amps that we'll be going through. So there's a couple of weeks. And I think really, I have to look through it, but through that, there's 4 primary circuits that we'll be studying the most, if you will. That'll basically get across the op-amp concept, the best for us. Because we have to look at linear and nonlinear applications of an op-amp. Linear will be easy, but the nonlinear will be a little more fun. So the way Frenzel, it looks like he has it broken up as chapter 34 is more linear applications for op-amps. And then chapter 35, we start looking at like the nonlinear applications of op-amps. And that's what, but I promise the labs won't be so, and you don't even have to set anything up physically now. You just have to go through and draw it out on a little simulator program, right? And I'm going to warn you guys, my young electricians here, that the world you're going into now more and more, a lot of instrumentation you're going to run into out there is going to be simulator style, where you're going to have like a simulator interface controlling large blocks of things. So it's actually, in some ways, is a benefit for you. See? And it all comes free. Nah. And then I discussed, I don't know if the administration gets a hold of you guys as far as what they decided. I did receive an email over the weekend that they did get official word that we're going to the pass-fail grading for this semester, for this 8 weeks. And then I think, or at least the plan is now, of course, who knows, right? But the plan is they're still going to continue on with online classes for the summer, and that'll be the same grade style too, where it's a pass-fail. But and that way it doesn't, I guess, from the way who the heck was explaining it, I think Cameron or somebody, but that the pass-fail won't affect your GPA overall, but you still get the college credit for this course and all that. I don't know. It doesn't make sense to me, but I'm an instructor. But no, in case anybody from administration didn't get a hold of you, I don't know how they're planning on rolling that out. And then I don't even know what the grade system is. I don't know if ABCs are considered pass and D's and F are fails, or how they do that. You know what I mean? We'll have to see. But they should have like an official rollout fairly soon now that we've gotten official word from the government and they got that all worked out. So that way they know what to do as far, because I guess the thing they were worried about was everybody's like financial aid, right? Because I know financial aid's weird when it comes to certain grade styles and this and that, but I guess everything's a good to go or something like that. I don't know if it's just an exception because of the coronavirus thing or what, but that's what they're kind of looking at. But that's really what I have for you guys today. Power amps, what we're going to look at, and I'll put up like I say, a formula sheet that specific for each type of power amp and whatnot. But you want your A? Yeah, I know. See, and that's the bad thing too, right? With the pass fail thing. Well, because if you're counting on the class as far as bringing your GPA up or something like that, then yeah, all it's going to do is maintain what your GPA is currently, I believe. But again, don't quote me on that. I'm not official. I just know that's the style we're going to. But do you guys have any questions on anything? Do you still want me to continue on? I'm going to post, like I say, 10-minute video demonstration, if you will, for each lab. Does that seem to help everybody? Like
Yeah.
what? Yeah, we like that.
Yeah, that's been helpful.
Okay. I'm sorry. Yeah, I didn't. Well, it's been a big curve on everybody. I know. Definitely putting a lot of work on me. I'll tell you what. But no, I kind of like running through and I guess if you, because I've been saving each circuit too, and I don't know how you review it. I've marked them as private, so I didn't want everybody looking at them, I guess. But if we were Facebook friends, you could see them, I guess. But no, we're not. We're not doing that. I promise. No. But yeah, I'll do the 10-minute demo for each one. We'll try to make this as painless as possible. I did post up the chapter 37 homework is up, and then I know the next 4 rounds of labs are posted up as well. If you guys want everything from now on, I'll even do that with these ones. Homework's in the homework tab, labs in the lab tab, and quizzes in the quiz tab. Is this right?
Yeah.
Yeah.
Yeah, that'll help.
All right. So I thought that was too confusing last time, so I was doing it the day-to-day thing for everybody. And see, what's that saying go? You can't please all the people all the time. You can, but all right. But yeah, you have any questions or anything you want to go over? I'll open it up as a forum. We can quit here. It's all up to you guys.
I'm good. I mean, if anybody else has anything.
I just want to confirm. So for the whole rest of the semester, after the quarantine's done, we're still doing online.
Yeah. As far as I know, at least from this point forward, everything the whole summer semester and the rest of this semester are all going to be online.
So fall back normal.
Hopefully. I mean, we're gonna have to see how this all plays out, Jared. Who knows? Virus might mutate and kill us all, and then there won't be nothing for fall. No, I'm just kidding. But we'll have to see. I mean, really, it's just, it's been pretty much a day-by-day basis, week by week, and seeing what happens by that point. I have no idea. Yep.
I had a question. So I was talking to somebody in financial aid. So, we all get charged a lab fee for being in the lab. They were saying they may refund us our lab fees since we're not actually in a lab.
Oh.
Did you hear anything about that?
No, I don't usually deal with the whole finances part. You guys do pay a lab fee?
Yeah, it's like $125 per class.
Really? Huh. Well, I would have meant. Well, I can't officially declare on that. I really, like I say, that would have to come more from. God, I'm not really even sure. You'd think it would definitely be somebody in the administration and over in the TLC center, right?
Yeah, because one of my roommates, we had a discussion about it. They supposed to refund us our lab fees because we're not technically in lab. Because Bradley They refunded all their students. They had labs. They refunded them their money. So we're trying to see if we're gonna get ours refunded
Right.
because we already paid for the last 8 weeks. So I want to get the refund for this 8 weeks.
Yeah, I'm not even sure who you. Well, you guys all have like, what do you call it? You have a financial advisor, right? Like a person, or do you just have a generic?
A generic like thing. You just go to the office and sign up.
Just whoever over there in the windows or whatnot.
Yeah.
Yeah.
You know, because I haven't even heard anything about that. I could try. I could send an email up the pipe, but I don't know. You know what I mean? I don't know how I get lost after a certain. What do they call that? It's above my pay grade. You know what I mean? But yeah, I could send an email up the pipe and see what kind of response I get back.
Okay.
And in fact, I'll do that today. I'll send it up to. Yeah, because I think Steve Flynn is still, for at least the next 8 weeks or next 5 weeks or whatever the heck, he's still the acting dean. But I do know we have a new. I don't know if you guys have seen that. We do have a new dean for AIT, and I can't even remember the person's name. Oh, good Lord. But we do. I guess they did hire a dean, so now after, I guess starting in the summer, we'll have an official, full-fledged AIT dean. But yeah, I'll send an email up to up the pipe and see what they say about that, Anthony, as far as the lab fee. I didn't even know anything about that. But any other questions you guys have, or we're all good? And then, you know how to get a hold of me. I might, oh, we'll have to see. I might go ahead and open up the tabs for the lab assignments so you can cut and paste your schematics into Blackboard. We could try that, and that way my email doesn't get overloaded and bombarded, because I still have a lot of, oh my God, I have so much sorting to do. But no, all part of the master plan. But all right, if you guys have no other questions, we're all good.
None today.
All right. Well, you guys know how to get a hold of me, and I usually, like I said, I try to respond back quick. If I don't, definitely worst case scenario, always text me. I usually get those. Remember, I'm old. I do take naps. But all right, guys, I'll see you on Wednesday.